Tonight, we're going to explore the distances in space. Not just the distance to the nearest star. The distance to the edge of our own galaxy and to the nearest galaxy beyond it. And what each of those distances actually means. Because we live in a universe where light, the fastest thing that exists, still needs years just to reach the nearest star and millions of years to reach the next galaxy over. A universe where the most distant galaxies we can see are already moving away faster than any signal we could ever send. The distances aren't just a travel problem for some future generation of engineers to solve. They reshape what we can see, what we can know, and what will ever be reachable from this planet. By the end of tonight, you're going to understand exactly how far the distances go at every scale, and why the more you understand them, the worse they get. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Start with the Moon. The Moon is the closest large natural object to Earth, sitting about 239,000 miles away on average. We've been there. We sent astronauts, landed them on the surface, and brought them back. It is the only other world human beings have ever stood on, and it took about 3 days to reach by spacecraft. 3 days to travel 239,000 miles. That feels significant until you understand what comes next, because the Moon is 1.25 light seconds from Earth. A signal traveling at the speed of light covers that distance in 1.25 seconds. During the Apollo missions, that delay was real and present in every conversation between the astronauts and mission control. Every exchange carried a 2.5-second round-trip lag at the speed of light. That is what close looks like in space. 1.25 light seconds. And from here, everything gets worse. Now go to Mars. Mars is often described as Earth's nearest planetary neighbor, though Venus actually comes closer to us at certain points in its orbit. But Mars is the one we're seriously trying to reach. The one we've sent the most spacecraft to. The one we're actually planning to send humans to. Mars orbits the Sun at an average distance of about 142 million miles. Earth orbits the Sun at about 93 million miles. The gap between us varies depending on where each planet is in its orbit. At closest approach, Mars gets to about 34 million miles from Earth. At farthest, when the two planets are on opposite sides of the Sun, the distance stretches to about 250 million miles. At closest approach, a signal traveling at the speed of light takes about 3 minutes to reach Mars. At farthest, about 22 minutes. 3 minutes. That sounds quick, but in practice, it means you cannot have a real-time conversation with anything on Mars. Every basic exchange is at minimum 6 minutes round trip. If something unexpected happens on the surface, if the rover encounters a hazard or a system fails, you won't know about it for 3 minutes. The response you send won't reach it for 3 more minutes after that. 6 minutes minimum per action-response cycle. Mission operations teams for Mars rovers have to plan every action in advance, send batches of commands, then wait for the rover to execute them and report back. It's not remote control. It's more like sending a letter. And this is the situation on Mars, our nearest serious target for human exploration. A signal there takes 3 minutes. Now, look outward. Past Mars, there's the asteroid belt, a ring of rocky bodies orbiting between Mars and Jupiter. Past that, Jupiter, the largest planet in our solar system. 11 times the diameter of Earth. More than 1,300 Earths could fit inside it. Jupiter orbits the Sun at an average distance of about 483 million miles. A signal from Earth to Jupiter takes between 33 and 52 minutes to arrive, depending on where both planets are in their orbits. Past Jupiter comes Saturn, famous for its extraordinary ring system, which spans about 170,000 miles in diameter. Saturn orbits the Sun at about 886 million miles. A signal takes roughly 70 to 87 minutes. Then Uranus, about 1.8 billion miles from the Sun on average. Signal time roughly 2.5 to 3 hours. Then Neptune, the outermost major planet, about 2.8 billion miles from the Sun. A signal from Earth to Neptune takes about 4 hours to arrive. We sent a spacecraft to Neptune. Voyager 2 launched in August of 1977 and arrived at Neptune in August of 1989. 12 years. For a single flyby. No stopping, no orbit, no landing. Just flying past the planet, close enough to photograph it and collect data, then continuing onward into the outer solar system. 12 years to reach Neptune for a single pass. And when Voyager 2 finally reached Neptune, the signal carrying the images and data back to Earth took about 4 hours to arrive. Every photograph came with a 4-hour wait. Every confirmation of a successful maneuver came with a 4-hour delay. But the scientists were overjoyed. It worked. After 12 years of travel, the spacecraft arrived at Neptune, essentially on schedule, performed its observations, and sent back images of a brilliant blue world and its largest moon, Triton, a frozen world with nitrogen geysers on its surface. Voyager 2 then continued outward, into the realm beyond Neptune, the Kuiper Belt, and beyond that, interstellar space. Today, Voyager 2 is roughly 12.5 billion miles from the Sun. Its signal takes about 17 hours to reach Earth. 17 hours. One way. A signal sent from Earth to Voyager 2 today takes 17 hours to arrive. If an engineer in California sends a command, they wait 17 hours for it to arrive, then wait another 17 hours for any confirmation to return. A total of 34 hours per command response cycle. And Voyager 2 is still, technically, a local object. It's still in the region of space, immediately surrounding our Sun. Still, not even close to the nearest star. Because here is the thing most people miss about the size of our solar system. When people say the solar system, they usually picture the Sun, the planets, maybe the asteroid belt. They picture an object you could fit inside a few billion miles. Pluto's orbit is about 3.7 billion miles from the Sun on average. And most people's mental model of the solar system ends somewhere around there. But that mental model leaves out 99% of the solar system, because the Sun's gravitational influence doesn't end at Pluto's orbit, not even remotely. Beyond the Kuiper Belt, extending out from about 50 astronomical units, there may be a region called the scattered disk, objects in highly elongated orbits, flung out from the Kuiper Belt by gravitational interactions with Neptune. Some of these objects spend most of their orbits far beyond Neptune, dipping in close only occasionally. Sedna, one of the strangest objects in the solar system, has an orbit that takes it out to about 937 astronomical units at its farthest. That's about 87 billion miles. Sedna takes roughly 11,000 years to complete one orbit around the Sun, and Sedna might be an inner Oort cloud object, the Oort cloud. This is where the solar system's true scale becomes apparent. The Oort cloud is a vast, spherical shell of icy bodies surrounding our solar system in every direction. We've never directly observed a single Oort cloud object. The objects there are too small and too far away for any telescope we've built. But we know the Oort cloud exists because of the evidence it sends us. Long-period comets. These are comets with orbital periods ranging from hundreds to millions of years. When we track their orbits backward, they originate from an enormous spherical region surrounding the solar system. The cloud of icy bodies they come from is the Oort cloud. Something perturbs them occasionally. A passing star, a slight gravitational nudge from within the cloud itself, and they fall inward. They spend hundreds or thousands of years falling toward the sun. When they finally arrive in the inner solar system, they develop the brilliant tails we see, and then they're gone again. Falling back out on orbits so elongated, they'll be gone for thousands more years. The Oort cloud is thought to begin at roughly 2,000 astronomical units from the Sun. 1 astronomical unit is the average distance from Earth to the Sun, 93 million miles. 2,000 astronomical units is about 186 billion miles, and the Oort cloud extends outward from there, all the way to roughly 100,000 astronomical units, about 9.3 trillion miles, nearly 1.6 light-years from the Sun. The outer edge of our solar system's gravitational reach is more than 1.5 light-years away. Now, consider Voyager 1. Currently, the most distant human-made object in existence, traveling at roughly 38,000 miles per hour. Voyager 1 will reach the inner edge of the Oort cloud in approximately 300 years, and it will spend approximately 30,000 years passing through it. 30,000 years, just to exit the outer gravitational boundary of our own star. We launched Voyager 1 in September of 1977. It will not clear our solar system for 30,000 years. And we launched it nearly 50 years ago, and it's been going the entire time. That is the scale of what we live inside, before we've even taken a single step toward another star. Now, we exit the solar system. We cross the Oort cloud. We leave the last of the Sun's gravitational influence behind, and we find ourselves in interstellar space, the space between stars. And the nearest star is Proxima Centauri, 4.24 light-years away. A light-year is the distance light travels in 1 year. Light moves at 186,000 miles per second. In 1 year, that works out to about 5,878 billion miles. Multiply by 4.24, and the distance to Proxima Centauri is roughly 25 trillion miles. That is the distance to the nearest star, our nearest neighbor in the entire galaxy, 25 trillion miles away. Now, put that number next to our best spacecraft. Voyager 1 is traveling at about 38,000 miles per hour. That's roughly 10.5 miles per second. Voyager 1 covers approximately 330 million miles per year. At that speed, pointed directly at Proxima Centauri, which it isn't, the journey would take approximately 78,000 years. 78,000 years. No stops. No adjustments. Just continuous travel at 38,000 miles per hour for 78,000 years. The entirety of recorded human history spans roughly 5,000 years. We would need to do that 16 times over to reach the nearest star at Voyager's speed. Civilization would have to rise and fall, and rise again, over and over, for as long as that. And Voyager 1 isn't even our fastest spacecraft. The Parker Solar Probe, launched in 2018, is designed to dive close to the Sun and study its outer atmosphere. During its closest passes, the Sun's gravity accelerates it to extraordinary speeds. At maximum, the Parker Solar Probe has reached about 430,000 miles per hour. That's our speed record. The fastest thing humanity has ever made move. At that speed, pointed at Proxima Centauri, the journey would take approximately 6,500 years. 6,500 years. The ancient Egyptians began building the Great Pyramid at Giza about 4,600 years ago. The entire span of recorded human civilization is roughly 5,000 years. Our fastest spacecraft needs more time than that just to reach the nearest star. And the Parker Solar Probe only achieves that speed by swinging close to the Sun. In interstellar space, without a star's gravity to accelerate it, it would be much slower. The real travel time at practical interstellar speeds would be far longer. This is not an engineering problem. This is not a limitation we can budget our way around. The distances involved are so extreme that nothing we've built or are planning to build could cross them in anything resembling a human timescale. We are, in a very specific and very real sense, trapped, not by walls, by the size of the universe and the limits of physics. This isn't a temporary situation. It's the nature of space. Let's spend some time with Proxima Centauri itself, not just as a number, but as a place. Proxima Centauri is a red dwarf star. Red dwarfs are the most common type of star in the Milky Way, making up about 70 to 75% of all stars in the galaxy. They're small, cool, and dim. Proxima has about 12% the mass of our Sun. Its diameter is about 14% of the Sun's diameter. It has a surface temperature of about 5,000 degrees Fahrenheit. The Sun's surface is about 10,000 degrees Fahrenheit. Proxima is cooler, dimmer. It emits only about 0.1% of the light our Sun produces. 0.1%. Proxima is so faint that even though it's the closest star to Earth, it is invisible to the naked eye. The nearest star to our planet cannot be seen without a telescope. That's how dim red dwarfs are. If you somehow flew to Proxima Centauri and orbited it, the sky would be a very different experience from Earth. The Sun would look smaller and dimmer, more orange-red than white. The spectrum of light would be shifted toward the red end. Photosynthesis, as we know it, would not work as efficiently. The system would be bathed in a different quality of light than anything on Earth. But Proxima Centauri does have at least one known planet, Proxima Centauri b. Discovered in 2016 using the radial velocity method, which detects the tiny gravitational wobble an orbiting planet creates in its host star. Proxima Centauri b has a minimum mass of about 1.27 times Earth's mass. It orbits within the habitable zone, the range of distances from a star where liquid water could potentially exist on a surface. But it's important to understand why this is more complicated than it sounds. Proxima Centauri b orbits its star at a distance of about 0.048 astronomical units, far closer than Mercury orbits our Sun. It completes one full orbit in 11.2 days. A year on Proxima Centauri b is 11 days long. At that distance, the planet is almost certainly tidally locked. one face always turned toward the star. One face permanently in darkness. The day side would be blasted with constant radiation. The night side would be frozen in permanent darkness. If any habitable region exists, it would be a narrow band around the terminator, the line dividing day from night. And Proxima Centauri is not a gentle star. Red dwarfs are known for powerful flares, sudden eruptions that can blast nearby planets with intense ultraviolet radiation and charged particles. Proxima has been observed flaring dramatically. In March of 2019, astronomers using the Atacama Large Millimeter Array observed Proxima emit a flare 1,000 times brighter than our Sun's most powerful flares. A flare 1,000 times more intense than anything our Sun produces. At that distance, the radiation hitting Proxima Centauri b during such an event would be devastating to any unprotected surface. Any life that might exist there would need substantial protection. Underground, perhaps, or in oceans deep enough to shield from radiation. The nearest star's nearest planet. And it's a place that would try very hard to end life as we know it. 25 trillion miles away. Proxima Centauri belongs to a larger system, the Alpha Centauri triple star group. The two other members, Alpha Centauri A and Alpha Centauri B, orbit each other at about 4.37 light-years from us. These two are Sun-like stars. Alpha Centauri A is slightly larger than our Sun, about 1.1 solar masses and about 1.5 times more luminous. Alpha Centauri B is slightly smaller and dimmer, about 9/10 of a solar mass and about half the Sun's luminosity. Alpha Centauri A and B orbit each other in an elliptical orbit. Their closest approach to each other is about 11 astronomical units, roughly the distance of Saturn from our Sun. At their farthest, they're about 36 astronomical units apart. One complete orbit takes about 80 years. Imagine looking up from Earth and seeing two suns in slow orbit around each other. That's the view from any planet in that system, though no confirmed planets around A or B have yet been found, despite intense searching. Proxima Centauri orbits both of them at an enormous distance, about 15,000 astronomical units from the AB pair. It takes Proxima roughly 550,000 years to complete one orbit around its two companions. 550,000 years per orbit. Proxima and the AB pair are so far apart within their own system that their gravitational bond was questioned for years. Some astronomers argued Proxima might just be passing through, not truly gravitationally bound. Recent measurements of proper motion, the slow drift of these stars across the sky over decades of observation, have confirmed that Proxima appears to be genuinely bound to the system, but the bond is tenuous. A passing star could potentially strip Proxima free. And if you stood on a hypothetical planet orbiting Alpha Centauri A and looked out at the night sky, you'd see our Sun, not as we see the Sun, as a faint star, a blue-white point of light in the direction of the constellation Cassiopeia, about the third brightest star in the sky. From that vantage point, you could look at it, point your finger at it, and it would be 25 trillion miles away, just sitting there, shining. Nothing between you and it but 4.25 light-years of vacuum. Cold, dark, radiation-threaded emptiness. And even at the speed of light, it would take 4 years to reach that dot. 4 years of travel to get from one neighborhood to the next. Let's step back and look at the neighborhood as a whole. Within about 16 light-years of our Sun, there are roughly 50 to 60 stars. That number seems like a lot, but the volume of space within 16 light-years is enormous. A sphere, 16 light-years in radius, has a volume of roughly 17,000 cubic light-years. 50 stars in 17,000 cubic light-years. That's about one star per 340 cubic light-years. They are not close to each other. Every star in our neighborhood is separated from every other star by years of light travel time. Barnard's star, a red dwarf about 6 light-years from the Sun, the second nearest star system to Earth after the 3 components of Alpha Centauri. Barnard's star is notable for having the highest proper motion of any star, meaning it moves across the sky faster than any other star relative to the background of more distant stars. It's traveling toward us. In about 10,000 years, it will be the nearest star to Earth, closer even than Proxima Centauri. Then it will continue its journey and pass by, slowly receding. Barnard's star may have at least one planetary companion, though the evidence is debated. Wolf 359, a red dwarf about 7.8 light-years away. So dim that even from Earth, you need a decent telescope to see it. It has about 9% the mass of the Sun. If you replaced our Sun with Wolf 359, the Earth would be as dark and frozen as Pluto is today. Sirius, 8.6 light-years away. The brightest star in Earth's night sky after the Sun. Sirius A is a brilliant blue-white star, about twice the mass of the Sun and roughly 25 times more luminous. It shines so spectacularly in our sky, not because it's extraordinarily powerful, but because at 8.6 light-years, it's relatively nearby. There are stars in the Milky Way thousands of times more luminous than Sirius. But they're so far away that they appear faint or invisible. Sirius has a companion, Sirius B, a white dwarf, the core remnant of a star that has exhausted its nuclear fuel. Sirius B is about the same diameter as Earth, but contains roughly the mass of our Sun. A teaspoon of Sirius B material would weigh about 15 tons on Earth's surface. The two stars orbit each other in an elliptical orbit with a period of about 50 years, and Sirius is 8.6 light-years away. Light takes 8.6 years to travel from Sirius to your eye. When you look at Sirius on a clear night, the light you're seeing left that star 8.6 years ago. Everything that has happened in your life in the past 8.5 years, Sirius hasn't heard about. Its light was already on the way before it happened. Epsilon Eridani, about 10.5 light-years away, one of the nearest Sun-like stars to Earth. It's slightly cooler and less luminous than our Sun, about 82% the solar mass and about 34% the luminosity. It has a confirmed planet, Epsilon Eridani b, detected by radial velocity measurements. The system also has at least one debris disk, a ring of rocky and icy material orbiting the star, similar to our asteroid belt and Kuiper belt. Tau Ceti, about 11.9 light-years away. One of the most studied nearby stars because it's one of the most Sun-like within a dozen light-years. It has multiple planetary candidates, though none have been definitively confirmed as habitable. These are our neighbors. The stars within 12 light-years, all unreachable. Every single one of them. With our fastest technology, the nearest would take over 6,000 years. The ones 12 light-years away would take over 18,000 years. We are surrounded by stars on all sides, and we cannot reach any of them. That is the state of human spaceflight. Not because we haven't tried hard enough, not because we haven't put enough money into it, because the distances involved are on a different scale entirely from anything our technology can currently address. And our neighborhood is still just a tiny local region within a galaxy so large it takes another breath just to describe it. The Milky Way, our galaxy. A barred spiral galaxy containing somewhere between 200 billion and 400 billion stars. The number range is not a sign of scientific imprecision. It reflects genuine measurement uncertainty. We cannot count the stars individually. We estimate the total mass of the galaxy, model what fraction of that mass is in different types of objects, and arrive at the estimate. 200 to 400 billion is the current best range. The galaxy is shaped like a flat disk with a central bar. The disk spans roughly 100,000 light-years in diameter. The central bulge, the thick region around the bar, is perhaps 10,000 light-years thick. The disk itself, where most of the stars and all the spiral arms are found, is much thinner. About 1,000 light-years thick on average. 100,000 light-years wide. About 1,000 light-years thick. A flat, spinning structure of stars, gas clouds, and dust orbiting around a central concentration of mass. Our Sun sits roughly 26,000 light-years from the galactic center, about halfway out. Not near the center, where stars are densely packed and radiation from Sagittarius A makes the environment hostile. Not near the outer edge, where the density of stars thins to almost nothing. In the middle zones. In a relatively quiet region, sometimes called the galactic habitable zone, where conditions might be most amenable to complex planetary systems. We orbit around the galactic center at roughly 483,000 miles per hour. One full orbit of the Milky Way, called a galactic year, takes about 225 million years. The last time the Sun was at its current position in its orbit around the galaxy, the Permian-Triassic extinction was underway on Earth, wiping out about 96% of all marine species and about 70% of all terrestrial species. That's how long a galactic year is. One orbit. 225 million years. The Sun has orbited the galaxy about 20 times since it formed. 20 galactic years. That's the Sun's age. The galactic center. 26,000 light-years from where we are. Hidden behind enormous clouds of gas and dust that block visible light almost completely. If you could see through those clouds, the galactic center would be the brightest object in our night sky by far. Thousands of stars packed tightly together. Enormous molecular clouds. Young hot stars forming from the compressed gas, and at the very heart of it all, Sagittarius A, a supermassive black hole. Its mass is approximately 4 million times the mass of our Sun. 4 million solar masses. The event horizon of Sagittarius A, the mathematical boundary beyond which nothing can escape, is roughly 15 million miles across. Our Sun is 865,000 miles in diameter. The event horizon of Sagittarius A is about 20 times wider than our Sun. But it has 4 million times the Sun's mass. The density is almost impossible to comprehend. Around Sagittarius A, A cluster of stars, called the stars, orbit at extraordinary speeds and distances. The star, S2, has been tracked since the 1990s. It has a highly elliptical orbit around the galactic center, with a period of about 16 years. At its closest approach, S2 passes within about 120 astronomical units of Sagittarius A. During that closest approach, S2 moves at roughly 4,600 miles per second. That's about 2.5% of the speed of light. A whole star moving at 2.5% of light speed. By tracking S2's orbit precisely over many years, astronomers could calculate the mass of the invisible object at the center. 4 million solar masses in a region smaller than our solar system. Only a black hole fits those numbers. In 2022, the Event Horizon Telescope collaboration released the first direct image of Sagittarius A. The image shows a ring of glowing material, heated to extreme temperatures as it spirals toward the event horizon, with a dark central region. The shadow of the event horizon itself. It's blurry, fuzzy. Not because the instruments are poor, because Sagittarius A is 26,000 light-years away, and it's about the angular size of a donut on the moon when viewed from Earth. The resolution required to image it is extraordinary. The Event Horizon Telescope accomplishes this by linking radio observatories around the world into a single virtual telescope, the diameter of Earth. Even so, the image is blurry, because it's 26,000 light-years away. The light in that image left the galactic center 26,000 years ago. When those photons began their journey toward Earth, the last ice age was still ongoing. Humans were painting animals on cave walls in France and Spain. Written language didn't exist. Agriculture was still thousands of years in the future. And the light from Sagittarius A was en route. Now, it arrives at our detectors. Now we call it a photograph. Everywhere you look in the cosmos, you are seeing the past. The deeper you look, the older the past. Our own galactic center is showing us a 26,000-year-old past, and the galactic center is our neighborhood. In cosmic terms, 26,000 light-years is local. The scale of the Milky Way itself deserves more attention. 100,000 light-years across. We have established that the nearest star is 4.24 light-years away. To get a feel for what 100,000 light-years means, consider this. If you could somehow travel at the speed of light, crossing the Milky Way from one edge to the other would take 100,000 years. 100,000 years at light speed. Our fastest spacecraft travel at a tiny fraction of the speed of light, well under 1/10,000th of 1%. At Voyager's speed, crossing the Milky Way from one edge to the other would take roughly 1.8 billion years. The current age of the universe is about 13.8 billion years. So, even at the pace of our fastest departing spacecraft, a single crossing of our own galaxy would consume a meaningful fraction of the entire age of the universe. One crossing of one galaxy. And there are 2 trillion galaxies out there. These numbers have passed beyond comprehension into something like a different category of reality. But they're accurate. That's what the Milky Way is. We live inside it. And we can't cross even a tiny fraction of it. The stars in the Milky Way are mostly orbiting around the galactic center. But they're not in rigid, fixed paths. Their orbits are complex. They bob up and down through the plane of the galaxy as they orbit. They're influenced by the gravity of giant molecular clouds and spiral arms, and they move relative to each other. Stars pass each other at cosmic slow-motion speeds. Our nearest stellar neighbor, Proxima Centauri, is currently at 4.24 light-years. But that distance is changing. All stars are in motion. In about 1 1/3 years, a red dwarf called Gliese 710 is expected to pass through the Oort cloud, coming within about 13,000 astronomical units of our Sun. That's close enough to significantly perturb the Oort cloud, sending swarms of comets into the inner solar system. The event won't be catastrophic on a short timescale, but it will reshape the cometary supply to the inner solar system for millions of years. Gliese 710 is currently about 62 light-years away, coming closer, slowly, on a timescale of tens of thousands of years. This is what cosmic neighborhood looks like over time. Stars drifting past each other. Gravitational influences redistributing material. The solar system's environment changing slowly over timescales we don't intuitively experience. Within the Milky Way, there are hundreds of billions of planets. We know this because of what we've found already. As of 2026, we've confirmed more than 5,500 exoplanets, planets orbiting other stars. The first confirmed detection came in 1992, when astronomers found planets orbiting a pulsar, a rapidly spinning neutron star. The first confirmed planet around a Sun-like star came in 1995. Since then, the pace of discovery has accelerated enormously. The Kepler Space Telescope, which operated from 2009 to 2018, stared at a single patch of sky containing about 150,000 stars. It looked for the tiny dip in starlight when a planet passes in front of its star. The transit method. Kepler found over 2,600 confirmed planets. And because it was looking at only a tiny slice of the sky, and because the transit method only detects planets whose orbits happen to be aligned with our line of sight, which is a small fraction of all planets, the implied total planet count in the galaxy is staggering. Statistical analysis of Kepler's data suggests that on average, every star in the Milky Way has at least one planet. Some stars have more. The galaxy contains more planets than stars. If the Milky Way has 300 billion stars, it has at least 300 billion planets. Possibly more. And of those 300 billion planets, roughly 1 billion are estimated to be rocky worlds in their star's habitable zone. 1 billion potentially Earth-like worlds in our galaxy alone. 1 billion. Every single one unreachable. Not just now, not just with current technology. Unreachable on any human timescale, with any foreseeable technology. Because each one of them is separated from us by light years. Hundreds of light years. Thousands. Tens of thousands. All of them orbiting stars that are impossibly far away. The most frustrating form of abundance the universe has ever offered. Billions of worlds. None of them accessible. All we can do is detect them, study them from afar, measure their atmospheres spectroscopically, infer their properties from the light their stars emit, and wonder. At the center of the Milky Way, the galactic center region, stars are packed much more densely than in the galactic suburbs where we live. Within a parsec of Sagittarius A, there are several million stars. A parsec is about 3.26 light-years. Within 3.26 light-years of the galactic center, several million stars. In our part of the galaxy, within a sphere 3.26 light-years in radius, there is exactly one star. Our Sun. The nearest other star, at 4.24 light-years, is just barely outside that sphere. The galactic center is so densely packed with stars that the night sky from any planet there would be hundreds of times brighter than our night sky. Stars would be visible in the daytime. The background radiation environment from all those nearby stars and from the activity of Sagittarius A would be far more intense. It would be a very different place to be. Violent, energetic, lit from all directions. 26,000 light-years away. Completely invisible to us in optical wavelengths. Hidden behind clouds of dust, so thick and dense that 100 times 100 light-years of interstellar medium lies between us and it. Step outside the Milky Way now. The Milky Way is not alone. It is part of a family of galaxies called the Local Group. A collection of galaxies gravitationally bound together, meaning they're close enough that their mutual gravity keeps them from being separated by the expansion of the universe. The Local Group contains more than 60 galaxies. The vast majority of them are small, dwarf galaxies. Collections of stars ranging from a few million to a few billion. Many of them are satellite galaxies of the Milky Way or Andromeda. The Milky Way has two prominent satellite galaxies visible from the southern hemisphere: the Large Magellanic Cloud and the Small Magellanic Cloud. The Large Magellanic Cloud is about 163,000 light-years away. It spans about 14,000 light-years across. It contains roughly 30 billion stars, and it is visible to the naked eye, appearing as a detached piece of the Milky Way. From the southern hemisphere, on a dark, clear night, you can see both Magellanic Clouds without a telescope, whole galaxies, visible with the naked eye. The Large Magellanic Cloud is remarkable for its star formation. It contains one of the most extreme star-forming regions known in the local universe, the Tarantula Nebula, a vast cloud of gas and dust where new stars are being born at an extraordinary rate. The Tarantula Nebula is about 1,000 light-years across. It contains hundreds of thousands of young, hot stars. If the Tarantula Nebula were as close to Earth as the Orion Nebula, the nearest large star-forming region to us, at about 1,300 light-years, the Tarantula Nebula would cast visible shadows at night from its glow. It would completely dominate the sky. But it's 163,000 light-years away. So it's a small, bright patch in the Large Magellanic Cloud. The Small Magellanic Cloud is about 200,000 light-years away, slightly smaller and dimmer than its companion. Both Magellanic Clouds are expected to eventually be absorbed by the Milky Way. Their orbits are decaying under gravitational interaction. In a few billion years, they will merge into the larger galaxy. The Local Group also includes several dozen smaller dwarf galaxies. The Sagittarius Dwarf Galaxy is actually being consumed by the Milky Way right now. It's so close, only about 70,000 light-years away in the direction of Sagittarius, that our galaxy's tidal forces are literally tearing it apart. Its stars are being stretched into long streams that wrap around the Milky Way. We know this because we can detect streams of stars in orbits that don't match the normal galactic rotation. Stars from Sagittarius Dwarf, pulled in, incorporated into the Milky Way. Our galaxy has eaten smaller galaxies before, and the process is still ongoing. And then there is Andromeda, Messier 31, our nearest large galactic neighbor, the other dominant member of the local group. It sits about 2.5 million light-years away. 2.5 million light-years. The Milky Way is 100,000 light-years across. The gap between us and Andromeda is 25 times the diameter of the Milky Way itself. Andromeda is a spiral galaxy, slightly larger than the Milky Way, spanning about 220,000 light-years in diameter. It contains roughly 1 trillion stars, maybe more. It has its own retinue of satellite galaxies. It has its own supermassive black hole at the center. Andromeda's central black hole has a mass somewhere in the range of 100 million times the mass of the Sun. Compared to the Milky Way's Sagittarius A, at 4 million solar masses, Andromeda's black hole is about 25 times more massive. The two galaxies are on a collision course. Not because either of them is aimed at the other, but because their mutual gravity is drawing them together. They are approaching at roughly 68 miles per second. In about 4.5 billion years, they will collide. The collision will be slow. Collision for galaxies is not like a crash between two cars. The stars inside each galaxy are so widely spaced that the probability of any individual star from one galaxy hitting any individual star from the other is essentially zero. What will happen is that the gravitational dynamics will be completely disrupted. Stars from both galaxies will be flung into new orbits. Some will be ejected from the system entirely. The beautiful spiral structures of both galaxies will be destroyed. Gas clouds from both galaxies will collide at high speeds, triggering intense bursts of new star formation. Over several billion years, the two galaxies will perform a kind of slow dance, passing through each other, swinging apart, then falling back together again. Each pass mixing the stars and gas more thoroughly. Eventually, perhaps 8 to 10 billion years from now, the merged object will settle into a large elliptical galaxy. A blob of hundreds of billions of stars, no longer spiral, rotating in complex, irregular orbits around the combined central mass. Our Sun will almost certainly survive. Its orbit will change. It may be flung to a very different part of the merged galaxy. Earth will likely survive too, though the sky will be transformed beyond anything recognizable. Instead of the flat band of the Milky Way crossing the night sky, there will be the chaos and brilliance of two merging galaxies. Star-forming regions blazing across the sky. Tidal streams of stars stretched in great arcs. A sky that would be considered spectacular from any vantage point. But Andromeda is 2.5 million light-years away. That is the most distant thing the human naked eye can see. Under dark skies, away from light pollution, Andromeda appears as a faint, elongated glow, a smudge, an oval blur in the direction of the constellation Andromeda. When you look at that smudge, the light entering your eye has been traveling for 2.5 million years. Those photons left Andromeda before Homo sapiens walked the Earth, before any human being existed. And they've just arrived. At you. Right now. 2.5 million years of travel. And we call it close. In the cosmic context, it is close. It's our next-door neighbor. And it's completely unreachable. Not in any meaningful human timescale. The local group spans about 10 million light-years from end to end. 10 million light-years of gravitationally bound galaxies, our gravitational home. And it fits inside a much larger structure, the Virgo supercluster. A supercluster is a collection of galaxy groups and clusters held together by gravity. The Virgo supercluster contains our local group and dozens of other galaxy groups, all gravitationally associated in a structure roughly 110 million light-years across. At the heart of the Virgo supercluster is the Virgo cluster itself, a rich galaxy cluster about 54 million light-years away, containing somewhere between 1,300 and 2,000 individual galaxies, not stars, galaxies. Each of those galaxies contains hundreds of billions of stars. The Virgo cluster spans about 8 million light-years in diameter. It's the dominant structure in our cosmic neighborhood. The Virgo cluster contains the most massive galaxy in our region of the universe, Messier 87, an enormous elliptical galaxy containing well over 1 trillion stars. At its center sits a supermassive black hole with a mass of approximately 6.5 billion times the mass of our Sun, 6.5 billion solar masses. For comparison, Sagittarius A, at the center of our galaxy, has 4 million solar masses. Messier 87's central black hole is over 1,000 times more massive than the one in our own galaxy. In April of 2019, the Event Horizon Telescope collaboration released the first ever direct image of a black hole. It was the black hole in Messier 87, a glowing orange ring of superheated gas surrounding a dark circular shadow. The image traveled 54 million light-years to reach our detectors. The light captured in that image left the vicinity of Messier 87's central black hole 54 million years ago. At that time, the asteroid that would end the non-avian dinosaurs' reign on Earth had struck 66 million years ago. Mammals were diversifying rapidly. Early primates existed, and the photons that would eventually form that historic image were just beginning their journey across the universe. In 2022, the Event Horizon Telescope published the image of Sagittarius A. 2 images now, 2 black holes. One 54 million light-years away, one 26,000 light-years away, both imaged from Earth. The resolution required is extraordinary. The angular diameter of Sagittarius A, as seen from Earth, is smaller than an orange sitting on the surface of the Moon. To image something that small required linking radio telescopes across the entire planet. Chile, Hawaii, the South Pole, Spain, Arizona. Together, they form a virtual telescope as wide as Earth. Even then, the images are blurry, because the distances are that extreme. The Virgo cluster's gravity pulls on the local group. Our entire collection of galaxies is falling toward the Virgo cluster, not fast enough to merge, not in any foreseeable time. The expansion of the universe is pushing the Virgo cluster away from us at the same time. But the gravitational influence is real and measurable. We're not stationary. We're in motion at every scale. The Earth moves around the Sun at about 67,000 miles per hour. The Sun moves around the center of the Milky Way at about 483,000 miles per hour. The Milky Way moves through the local group. The local group falls toward the Virgo cluster at some hundreds of miles per second. And the Virgo cluster and everything else is streaming towards something much larger. In 2014, a team of astronomers led by Brent Tully at the University of Hawaii published a paper that redrew the map of our cosmic home. They mapped the gravitational flows of galaxies across our region of the universe. The way galaxies drift is not random. They flow toward concentrations of mass, like water running downhill. By mapping the peculiar velocities, the motions of galaxies beyond what the overall expansion of the universe would predict, they could trace the gravitational basin that our galaxy and millions of others all share. They named it Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea spans roughly 500 million light-years. It contains about 100,000 galaxies. Its total mass is estimated at 10 to the power of 17 solar masses, 100 million billion times the mass of the Sun. Our Sun is one star among 300 to 400 billion in the Milky Way, which is one of 100,000 galaxies in Laniakea, which spans 500 million light-years. The Milky Way's position within Laniakea is equivalent, roughly, to being one house in a country. Everything in Laniakea, the Milky Way, the local group, the Virgo cluster, the Virgo supercluster, everything within 500 million light-years in a specific direction is all part of the same vast gravitational structure, all falling slowly toward a concentration of mass that sits within Laniakea. That concentration is called the Great Attractor. It sits roughly 150 to 250 million light-years away from us. We're moving toward it at roughly 370 miles per second. Not just our galaxy. Hundreds of thousands of galaxies, all streaming toward the same gravitational basin. The Great Attractor was hypothesized in the 1980s, based on measurements showing that galaxies in our region of the universe were all moving in the same general direction, and not in the direction the overall cosmic expansion would predict. Something was pulling them. Something massive. But we couldn't see it. Because the Great Attractor sits almost exactly behind the zone of avoidance, the densest part of the Milky Way's disk, where gas and dust are so thick that visible light can't get through. We were being pulled towards something we couldn't see. Eventually, using radio and infrared wavelengths that penetrate the dust better, astronomers mapped the region and found it, the Norma cluster, a massive galaxy cluster at the approximate center of the Great Attractor region, and around it, a larger structure sometimes called the Norma supercluster or the Great Attractor region, containing many other clusters and groups. All of it converging. All of it pulling everything nearby inward. And even the Great Attractor is falling towards something larger. There are structures called superclusters of superclusters or complexes. The Laniakea supercluster is falling toward the Shapley supercluster, the largest concentration of mass in the nearby universe. The Shapley supercluster sits about 650 million light-years away. It contains dozens of galaxy clusters, roughly 10 times the mass of Laniakea. Everything cascades. Every structure falls toward a larger one. Galaxies fall into clusters. Clusters fall into superclusters. Superclusters fall toward larger concentrations. The gravitational hierarchy of the universe keeps going up in scale, and at the very top of that hierarchy is the cosmic web, the largest structure in the observable universe. Zoom out far enough. Look at the observable universe as a whole. Not individual galaxies, not individual clusters, the whole thing at once. What you see is a network, a vast, three-dimensional network of filaments and sheets with enormous empty regions between them. The filaments are long threads of matter, hundreds of millions of light years long, containing chains of galaxy clusters and groups. The sheets are thin, two-dimensional concentrations of matter, galaxies arranged in flat walls. The nodes, where filaments and sheets intersect, are the densest places. Galaxy clusters, superclusters, the most massive gravitational concentrations in the universe. And between all of this are the voids. Enormous regions of space, nearly devoid of galaxies. The voids can be hundreds of millions to billions of light years across. The Boat's void, a region of space about 330 million light years wide. Discovered in 1981 when astronomer Robert Kirshner and his colleagues were mapping galaxies in that direction. They expected to find hundreds of galaxies. They found almost none. Just 8 galaxies in a region where hundreds should have existed. 330 million light years of near emptiness. If the Milky Way were at the center of the Boat's void, we wouldn't have known other galaxies existed until the 20th century. The nearest galaxies would have been so far away that only the most powerful modern telescopes could detect them. We'd have thought we were alone in the universe. The Eridanus supervoid may be even larger. Some estimates put it at roughly 1 billion light-years across. 1 billion light-years of space with almost nothing inside it. The voids are not truly empty. Cosmic rays pass through them. Photons cross them. Dark matter likely threads through them in dilute concentrations. But ordinary matter, the stuff that forms galaxies and stars and planets, is essentially absent. The voids are the scars of the early universe. In the very first fractions of a second after the Big Bang, tiny quantum fluctuations created slight variations in density. Some regions were slightly more dense, some slightly less. Over billions of years, gravity amplified these differences. The overdense regions attracted more matter. The underdense regions lost matter. The slight initial differences became the enormous voids and filaments we see today. The cosmic web is a direct consequence of the Big Bang and gravity acting for 13.8 billion years. It's not something designed. It's not something placed. It emerged from physics. And it spans the entirety of the observable universe. Every direction you look, billions of light years in every direction, the pattern repeats. Filaments and voids. Nodes and sheets. The cosmic web, from one horizon to the other. The cosmic web is also one of the most powerful confirmations that our understanding of the universe is correct. We can simulate it. Give a computer the initial conditions of the universe, as measured from the cosmic microwave background, the ancient light from the Big Bang that we can still detect. Feed in the laws of physics. Let it run for the equivalent of 13.8 billion years of cosmic evolution. And the simulation produces a cosmic web that matches what we observe. The illustrious simulation, the Eagle simulation, the Millennium simulation. All of them produce universes that look like ours. Filaments in the right places. Voids in the right places. Galaxy clusters at the right nodes. The right distribution of galaxy sizes and types. The simulations match observations not because the models were tuned to match, but because the physics is right. Gravity acting on the density fluctuations of the early universe naturally produces the cosmic web. It couldn't produce anything else. The universe we observe is consistent with a universe born in a hot, dense, rapidly expanding state and evolved under gravity and dark energy for 13.8 billion years. The cosmic web is the universe showing us its own history. Now come to the scale that encompasses all of this. The observable universe. This phrase is precise. Observable means the region of space from which light has had enough time to reach us since the Big Bang. Not everything that exists. Not everything that has ever existed. Just the region from which light could have traveled to our position since the universe began. The universe is approximately 13.8 billion years old. If the universe were not expanding, the observable universe would be a sphere 13.8 billion light years in radius. But the universe is expanding, and that changes everything. When the most distant galaxies we can see emitted their light, they were far closer to us than they are now. The universe was much smaller. Space was compressed. As that light traveled toward us, over billions of years, space expanded. The galaxy was carried away from us by the expansion of space, not the galaxy moving through space. Space itself growing between us and it. By the time that ancient light reaches us today, the galaxy that emitted it is now much farther away than the distance the light traveled. When you account for the expansion of the universe throughout its entire history, the edge of the observable universe, the farthest point from which any light has ever reached us, is currently about 46 billion light-years away, in every direction. The observable universe is therefore a sphere about 93 billion light-years in diameter. Within that sphere, astronomers estimate there are about 2 trillion galaxies. 2 trillion. 2 followed by 12 zeros. 2 million. Each one containing hundreds of billions to trillions of stars. The total number of stars in the observable universe is estimated at around 200 sextillion, 2 times 10 to the 23rd power, a 2 followed by 23 zeros. If every star were a grain of sand, you would need roughly 10 Olympic-sized swimming pools filled to the brim to hold them all. And each of those grains of sand would represent a star like our sun or larger, with potentially planets around them, 200 sextillion of them. And we cannot reach any of them. Not one. With anything we have built, with anything we're planning to build, every single one of those 200 sextillion stars is beyond our reach. The ones at the edge of the observable universe are so far away that light from them left before our planet existed. Long before. The universe was less than 1 billion years old when the light we're now seeing from the most distant galaxies began its journey. The solar system didn't form until the universe was about 9 billion years old. Those photons had been traveling for 9 billion years before Earth was even born, and they arrived here. They've reached us, carrying information from an era we can never visit, from objects we can never reach, from a time so remote it might as well be a different universe. And our telescopes catch them, and we look, and we try to understand. But even this, even the 93 billion light-years of the observable universe is likely just a fraction of what's actually out there. Because the observable universe is defined by a practical limit, not a physical edge. There's no wall, no boundary, no actual end. Just the furthest distance from which light has had time to reach us. Beyond that distance, there is more universe. We just haven't received light from it yet. The universe could be vast but finite, far larger than the observable portion, or it could be infinite. The geometry of the universe offers some guidance. Current measurements strongly suggest the universe is geometrically flat. Not flat like a sheet. Flat in the mathematical sense of having zero curvature. In a flat universe, parallel lines remain parallel forever, and the geometry of space is Euclidean at the largest scales. A flat universe, by the mathematics of general relativity, is either infinite or so large that any curvature it might have is smaller than our instruments can detect. The Planck satellite measured the universe's curvature to within about 0.5%. The result, flat. As flat as we can measure. This means the universe is almost certainly enormous. Possibly infinite. If it's infinite, every possible configuration of matter repeats. Infinitely many times. In an infinite universe, somewhere, there is another galaxy identical to the Milky Way. Another solar system identical to ours. Another Earth. Another version of every person reading this. Not similar. Identical. The mathematics demands it if the universe is infinite and the laws of physics are uniform. Because matter is quantized, there are only a finite number of ways to arrange particles in any finite volume. In infinite space, every finite arrangement must repeat. An infinite number of times. This is not philosophy. This is the logical consequence of an infinite universe with finite quantum states. Whether the universe is actually infinite, we cannot know. The observable universe is the limit of what we can see. Everything beyond the particle horizon is invisible to us. Not because there's nothing there, because the light hasn't arrived. It's still traveling, potentially from a universe vastly larger than anything our instruments can access. There is one more thing about the expansion of the universe that changes everything. The expansion is not just continuing, it is accelerating. In 1998, two independent teams of astronomers were studying Type Ia supernovae. These are stellar explosions that occur in binary star systems when one star, a white dwarf, accumulates so much mass from its companion that it explodes. The explosion is powerful, consistent, and can be seen from billions of light years away. Because Type Ia supernovae all reach roughly the same peak brightness, they're useful as distance indicators. By comparing how bright they appear to how bright they actually are, you can calculate how far away they are. By measuring their redshift, how much their light has been stretched to longer wavelengths by the expansion of space, you can determine how fast they're receding. Both teams expected to find that the expansion was decelerating. Gravity, after all, should be pulling everything back together. The expansion started with the Big Bang. Gravity should be slowing it. Everyone knew this. The only question was how fast it was decelerating. Both teams found the same shocking result. The distant supernovae were fainter than expected. They were farther away than they should be if the expansion was slowing down. The universe's expansion is not decelerating. It's speeding up. Distant galaxies are receding from us faster and faster. The expansion is accelerating. Something is driving that acceleration. We call it dark energy. We have no satisfying explanation for what dark energy actually is. It could be the intrinsic energy of empty space, what Einstein called the cosmological constant, a property of space-time itself that produces a repulsive effect at large scales. It could be some kind of scalar field permeating the universe. It could be something completely outside our current theoretical framework. What we know is that dark energy makes up roughly 68% of the total energy content of the universe. Dark matter makes up about 27%. Ordinary matter and energy, everything made of quarks and leptons and photons, everything we can directly detect and interact with, makes up about 5%. 5%. We understand about 5% of the universe in any direct sense. The remaining 95% is two forms of mystery. One that prevents galaxies from flying apart. One that is actively pushing everything apart, faster and faster. We are passengers in a universe we don't fundamentally understand. And the accelerating expansion has a direct consequence for what we can see and what we can ever hope to see. There is a distance from us at which galaxies are receding faster than light, not moving through space faster than light. Space itself is expanding between us and them faster than light can cross it. Currently, that distance is roughly 16 billion light-years. Beyond 16 billion light-years, galaxies are receding from us at superluminal speeds. The light they're emitting right now is effectively running in place. It's moving toward us at the speed of light, but space is growing between us and it at the speed of light. The light will never arrive. Those galaxies are already beyond our reach. Not just physically. They are beyond reach, even for information. We will never see them. Not with any telescope. Not in any future. And as the expansion accelerates, that boundary creeps closer. Galaxies currently within our observable universe will eventually cross that threshold. Their light will be stretched to longer and longer wavelengths. Infrared, microwave, radio frequencies too weak to detect. Silence. They'll fade from view. Not because they were destroyed, because the universe expanded too fast for their light to reach us. And this leads to one of the most sobering ideas in all of cosmology. There is a number called the reachable universe. It is the subset of the observable universe that we could theoretically reach, even with perfect technology, even traveling at the speed of light, starting today. And the reachable universe is far smaller than the observable universe. The observable universe contains about 2 trillion galaxies. The reachable universe contains only a few billion. Everything else, the overwhelming majority of those 2 trillion galaxies, is already beyond reach, already receding faster than any signal we could send, already lost to us no matter what we do. The universe shows us far more than we could ever touch. What we can see and what we can reach are 2 completely different things, structurally decoupled, separated by the expansion of space itself. And the gap between them only grows. As time goes on, the reachable universe shrinks. In billions of years, from our position, it will have shrunk down to just the galaxies of our own local group, perhaps 50 gravitationally bound galaxies. Everything beyond that will have accelerated permanently out of reach. In roughly 100 billion years, if dark energy remains constant, essentially all the galaxies we can currently observe will have been pushed beyond the cosmic event horizon. An observer then would look out into the cosmos and see only the merged remnant of the Milky Way and Andromeda, the Milky galaxy, surrounded by a handful of satellite galaxies. The rest, the 2 trillion galaxies, the cosmic web, the great voids and filaments, all gone from view, pushed beyond the horizon by the relentless acceleration of space. That future observer would have no evidence that any of this exists. They would construct cosmological models from the little they could see, and they would be catastrophically wrong about the scale of reality. They would have no way to know it. We are living in a fortunate moment. The universe is young enough that the expansion hasn't yet erased the evidence. We can still see the cosmic web. We can still observe 2 trillion galaxies. We can still measure the large-scale structure that tells us the universe's history. That window is open now. It will not stay open forever. Not in any cosmological sense. This is a brief, privileged moment in the life of the universe. And we happen to be here for it. There is one final dimension of cosmic distance that most people never fully reckon with. The fact that distance and time are inseparable. When you look at any object in the universe, you are not seeing it as it is right now. You are seeing it as it was. The light took time to travel. The farther away the object, the older the light. The more distant the past you're observing. When you look at the moon tonight, the light hitting your eyes left the moon 1¼ seconds ago. The moon you're seeing is the moon from 1¼ seconds in the past. That's nothing. Imperceptible, but physically real. When you look at the sun, the light left the sun's surface about 8 minutes and 20 seconds ago. The sun you're seeing is the sun from 8⅓ minutes in the past. If the sun somehow ceased to shine at this very moment, you would not know for 8⅓ minutes. The sky would stay bright for 8 more minutes. You'd be looking at a past sun that no longer existed, not knowing yet that it was gone. The light from Jupiter, depending on the positions of our orbits, left that planet between 33 and 52 minutes ago. Neptune, about 4 hours. Voyager 1, roughly 22 hours. The nearest star, Proxima Centauri, 4 years and 3 months. Sirius, 8.6 years. The Orion Nebula, about 1,300 years. The center of the Milky Way, 26,000 years. Andromeda, 2.5 million years. The Virgo cluster, about 54 million years. The farthest galaxies we've observed, about 13 billion years. Every one of these is a window into the past. The sky is not a single moment. It is a layered exposure spanning the entire history of the universe. The stars you can see with your naked eye are nearby, their light relatively recent. The faint smudge of Andromeda is 2.5 million years old. The cosmic microwave background, the oldest light in the universe, the thermal glow of the Big Bang, is about 13.8 billion years old. It fills the entire sky uniformly, coming from every direction, the fossil radiation of the primordial fireball. When you look at the deep sky, you look back in time. And the farther back you look, the more different the universe was. The most distant galaxies we've imaged with the Hubble Space Telescope and the James Webb Space Telescope are not mature spirals and ellipticals. They're small, irregular, often violently star-forming objects. The universe, in its youth, was different. The galaxies were different. The conditions were different. By looking out in distance, we look back in time. We can observe cosmic history directly, not infer it, not model it, actually see it. Galaxies as they appeared 1 billion years after the Big Bang, 2 billion years, 5 billion years, 10 billion years. The entire evolutionary history of galaxies laid out across the sky, one distance corresponding to one era. This is one of the most remarkable features of the cosmos. it has kept a visual record of its own history, and we have instruments sensitive enough to read it. The James Webb Space Telescope, launched in December of 2021, is the most powerful space telescope ever built. It observes in infrared wavelengths, which allows it to see the light from very distant galaxies that has been redshifted out of the visible range by the expansion of the universe. In its first months of operation, it imaged galaxies that formed within just a few 100 million years of the Big Bang. Galaxies from when the universe was less than 4% of its current age. And it is finding things that are challenging some aspects of our models of galaxy formation. Galaxies that are larger and more mature than we expected at that epoch, which suggests there may be aspects of the early universe we don't fully understand yet. The distances are so large that even our best theoretical models have gaps. And the universe is old enough that 13.8 billion years of history is encoded in the light we receive from different distances. Every photon we catch tells us something about where it's been, about the universe it crossed, about the era it came from. Distance and time, inseparable. The universe's past, written in light. And we are here reading it. So stand back from all of this. From the moon at 239,000 miles. From Mars at 34 million miles at closest. From Neptune at 2.8 billion miles. From the outer Oort cloud at 9 trillion miles. From Proxima Centauri at 25 trillion miles. From the Milky Way at 100,000 light-years wide. From Andromeda at 2.5 million light-years. From the Virgo cluster at 54 million light-years. From Laniakea at 500 million light-years across. From the observable universe at 93 billion light-years. From the actual universe, unknown, vast, possibly infinite. All of these numbers are accurate, verified, measured by human instruments and human minds. And what they describe is a reality that should fundamentally change how you see where you are. You are here, on a small, rocky planet, orbiting a medium-sized star, in the suburbs of one of 400 billion stars in a galaxy called the Milky Way, a galaxy that is one of 2 trillion in the observable universe, in a universe that is almost certainly far, far larger than the observable portion, surrounded on all sides by distances so vast they reduce every ambition of travel we've ever had, to something almost comically modest. The moon took us about 3 days to reach. Mars would take months. The nearest star would take tens of thousands of years with our fastest craft. The center of the Milky Way would take hundreds of millions of years. Andromeda would take billions of years. The distances in space are not just large. They are in a different category from everything human civilization has ever encountered. They are cosmic. And that word means something specific. Cosmic distances are not simply big distances. They are distances at the scale of the universe itself. They are not distances that can be conquered by more fuel or faster engines or better technology, at least not with anything our physics currently permits. They are distances that place most of the universe permanently beyond our reach. Not our reach this decade. Not our reach this century. Our reach permanently. Or at least for any time scale that civilization as we know it could endure. And yet, we know all of this. That is the thing that deserves the most attention. not the distances themselves. The fact that we've measured them. The fact that a species that evolved on one small planet, with brains evolved for hunting and gathering on African savannas, has somehow developed the mathematics and technology to measure the size of the universe, to map the cosmic web, to calculate the distance to the farthest galaxies, to detect the cosmic microwave background and read the history of the Big Bang in its temperature fluctuations, to image black holes at the center of galaxies 54 million light-years away, to photograph the rings of Saturn and the storms of Jupiter and the canyons of Mars and the methane lakes of Titan. We have never physically left the Earth-Moon system. Every human being who has ever lived has spent their entire life within a few thousand miles of Earth's surface. But we've mapped a universe 93 billion light-years across. We've reconstructed its history from the first fractions of a second after the Big Bang. We've identified 2 trillion galaxies we'll never visit. We've measured the composition of atmospheres on planets around other stars. We've detected gravitational waves from black hole mergers a billion light-years away. Something on this tiny, isolated planet looked out at the cosmos and said, "I want to know how big this is," and figured it out. Not all of it. There are still enormous gaps. Dark matter and dark energy remain deeply mysterious. The nature of the Big Bang itself, what happened in the very first moments, is still beyond our current physics. Whether the universe is finite or infinite remains unknown. Whether there is other life anywhere in those 2 trillion galaxies remains an open question. There is so much we don't know. But we know enough to understand the scale. Enough to know that we are very small. Enormously small. And that knowing that is itself an extraordinary achievement. Communication across these distances tells its own story. Because we've sent things. We've launched spacecraft. We've transmitted signals. And the distances have pushed back at every step. In 1972 and 73, NASA launched Pioneer 10 and Pioneer 11. Spacecraft designed to study the outer solar system and then travel beyond it. Pioneer 10 became the first spacecraft to cross the asteroid belt, the first to conduct a close flyby of Jupiter. And then it kept going, outward, into the outer solar system, past Saturn and Uranus and Neptune, into interstellar space. Pioneer 10's signal was last detected in January of 2003. At that point, the spacecraft was about 80 astronomical units from the Sun, about 7.4 billion miles out. A signal traveling at the speed of light took about 11 hours to travel from Earth to Pioneer 10. The signal was too faint for us to hear anymore after that. Not because of any failure on the spacecraft, because it had traveled so far that even the power of our best receivers couldn't pick it up. The transmitter on Pioneer 10 produces about 8 watts of power, roughly what a low-energy light bulb uses, across 7.4 billion miles. The signal spreads out across an enormous sphere as it travels. By the time it reached Earth, the power per square meter of signal was vanishingly small. The 26-meter Deep Space Network antenna receiving it was collecting a signal 17 billion times fainter than a watch battery produces. And even that was pushing the limits. Pioneer 10 is now roughly 130 astronomical units from the Sun and still traveling. Silent now, but still out there. Voyager 1 and Voyager 2 are still communicating with us. Just barely. The 26-meter dishes of the Deep Space Network receive their signals, but the signals are growing weaker each year. As the spacecraft travel farther, the signal spreads over a larger sphere. The power received per square meter drops with the square of the distance. Double the distance, reduce the received power to 1/4. Triple the distance to 1/9. The drop-off is relentless. At some point in the early to mid-2030s, Voyager 1's power supply will fall too low to operate any scientific instruments. The radioisotope thermoelectric generator produces electricity from the decay of plutonium-238. That decay produces heat. The heat is converted to electricity, but the plutonium is slowly running out. The power has been declining since launch. At some point, the voltage will drop below the threshold needed to operate the instruments. Then, the transceivers. And Voyager will go silent. Still traveling. Still moving outward through interstellar space at 38,000 miles per hour. But silent. No longer sending data back. No longer telling us anything. Just a small metal object about the mass of a compact car drifting through the darkness between stars, without a signal, without a name, to the universe. Just another object in interstellar space, probably forever. In about 40,000 years, Voyager 1 will make its closest approach to a star other than the Sun. A small red dwarf called AC plus 7938888. It will pass within about 1.6 light-years of that star. 1.6 light-years. Still not close enough to enter that star's planetary system, if it has one, just passing by. At 38,000 miles per hour. 40,000 years from now. And in 300,000 years, Voyager 1 will pass about 2 light-years from the star Proxima Centauri. Not into the system. Just nearby, by cosmological standards. 2 light-years is not nearby. 2 light-years is an enormous distance. But it's the closest Voyager 1 will come to another star in the next 1,000,000 years or so. And in 1,000,000 years, Voyager 1 will have traveled about 57 light-years from Earth. 57 light-years. In 1,000,000 years of continuous travel, the Milky Way is 100,000 light-years across. After 1,000,000 years of travel, Voyager will have crossed less than 0.06% of the galaxy's diameter. Less than 0.1%. After 1,000,000 years of non-stop flight, the distances are not large. The distances are beyond categories that include large. Here's another way to feel the scale of interstellar distance. Think about what we can actually observe in the night sky. With the naked eye, under perfect conditions, the faintest stars you can see are about magnitude 6. Astronomers use a counterintuitive scale for brightness. The brighter the object, the lower, or even more negative, the number. The full moon is about magnitude minus 12.6. Venus, at its brightest, is about minus 4.6. Sirius is about minus 1.46. The faintest stars visible to the naked eye in a dark sky are around magnitude 6. With a pair of binoculars, you can see stars to about magnitude 9 or 10. With an amateur telescope, to about magnitude 12 or 13. With the Hubble Space Telescope, to about magnitude 31. Magnitude 31. That corresponds to stars and galaxies almost impossibly faint. Each step of 5 magnitudes represents a factor of 100 in brightness. So magnitude 31 is 100 times, 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 compared to magnitude 1. That's 10 to the 14th power dimmer than a first magnitude star. 10 100,000 trillion times dimmer. And at that sensitivity, the Hubble can see galaxies 13 billion light-years away. Galaxies whose light left before our solar system formed. 13 billion years of travel. And the photons are still just barely detectable. That's the scale of the distances, combined with the inverse square law. Light from an object spreads out spherically as it travels. The farther it goes, the more area the light is spread over. The intensity at any point decreases with the square of the distance. Double the distance, 1/4 the brightness. Triple, 1/9. 10 times as far, 1/100th as bright. 100 times as far, 1/10,000th as bright. 1 billion light-years away, incomprehensibly dim, but detectable, barely, with the most powerful instruments we've ever built. And those instruments are showing us the cosmos at its earliest, most distant epochs. The James Webb Space Telescope has now imaged galaxies from when the universe was roughly 200 million years old. Less than 2% of the current age of the universe. Galaxies that formed almost right away. That shouldn't be possible, according to some models of galaxy formation. We expected the early universe to be filled with small protogalactic clumps slowly assembling into galaxies over billions of years. Instead, we're finding galaxies that appear surprisingly massive and mature at very early times. The universe may have assembled structure faster than our models predicted. The distances, in this case, are not just showing us how far things are. They're showing us that our understanding of the early universe may need revision. The cosmos, at its most remote, is still surprising us, still teaching us, still revealing that what we thought we knew was incomplete. Think about what would have to be true for interstellar travel to become a real possibility. Not in the incremental improvement sense. Not, maybe, with better rockets. In the actual physics sense. What would we need? At the most basic level, we need a way to move a payload from one star to another in a reasonable fraction of a human lifetime. Let's say, within about 100 years. 100 years is a long time, but it's within a human timescale. A person could devote their life to the mission and live to see the destination. To cross 4 light years in 100 years, you need to travel at 4% of the speed of light. 4%. That sounds small. 4% of 186,000 miles per second is about 7,400 miles per second. About 26 million miles per hour. Our current speed record, the Parker Solar Probe at its fastest, is about 430,000 miles per hour. To travel at 4% of light speed, we need to go about 60 times faster than our current record. 60 times faster, not 4 times, not 10 times. 60 times. And the Parker Solar Probe achieves its top speed only during brief gravitational maneuvers near the Sun. A spacecraft traveling to another star can't use that trick. The rocket equation is the fundamental problem. To go faster, you need more fuel. But carrying more fuel makes you heavier, which means you need even more fuel to accelerate the extra mass, which makes you heavier still. There's a brutal exponential relationship between your final velocity and the amount of fuel you need to carry. To reach 4% of light speed with a conventional rocket, you'd need to carry so much fuel that the mass of the spacecraft would be almost entirely fuel. The ratio of fuel mass to payload mass would need to be enormous. Numbers so large that the engineering becomes essentially impossible. This is called the Tsiolkovsky rocket equation problem. It's why chemical rockets can't get us to other stars, and why even nuclear rockets face enormous challenges. Theoretical alternatives exist. The Bussard ramjet, a spacecraft with a giant electromagnetic funnel that scoops up interstellar hydrogen, uses it as fuel in a nuclear fusion reactor, and accelerates. The interstellar medium, despite being very thin, contains hydrogen, about 1 atom per cubic centimeter on average. In principle, a ramjet could scoop this up and fuel itself. You wouldn't need to carry fuel. You'd gather it as you go. The problems are considerable. The magnetic funnel required would need to be enormous, hundreds of miles across. The drag from the interstellar medium at high speeds would likely offset the thrust from the collected hydrogen. The densities of hydrogen in the interstellar medium may be too low for the concept to work efficiently. And fusion of proton-proton hydrogen, the most common form, is extremely difficult to sustain. The Sun manages it. But the Sun uses an enormous mass and billions of years. A spacecraft reactor is neither. Still, theoretical concepts like the Bussard ramjet at least point toward the possibility, at least show that the laws of physics might permit something. More recent concepts include laser sails, a spacecraft with an enormous reflective sail, no engine of its own, no fuel. Instead, a powerful laser array on Earth, or in orbit around the Sun, fires a continuous beam at the sail. The pressure of the light accelerates the sail and its payload. The Breakthrough Starshot initiative is seriously pursuing this concept. The proposed design calls for a sail only a few meters across, carrying a tiny payload, a chip with cameras and instruments weighing only a few grams, and a laser array producing 100 gigawatts of power, illuminating the sail for a few minutes. At that power level, the tiny sail and payload could be accelerated to about 20% of the speed of light. 20%. At 20% of the speed of light, the journey to Proxima Centauri would take about 21 years. 21 years. For a chip-sized probe, with no ability to slow down. It would fly through the Alpha Centauri system at 1/5 the speed of light, taking images and data as it passes, sending the data back at the speed of light, which would take 4.24 years to arrive. The total time from launch to receiving data, about 25 years. The problems are numerous. The laser array doesn't exist. 100 gigawatts is enormous. The entire electrical output of a medium-sized country, for minutes, focused on a tiny sail. The optics required to keep such a beam focused across the distance needed to accelerate the sail are extraordinary. A sail, moving at 20% of light speed, would be struck by interstellar dust grains with enormous kinetic energy. Each grain, tiny as it is, hits with the force of a small bullet at that speed. The sail material would need to withstand constant bombardment, and slowing down at the other end is simply not possible with a laser sail. There's no laser array at Proxima Centauri to slow the probe. It flies through at 20% of the speed of light and keeps going. You get seconds to collect data, maybe minutes. Then it's gone. And the data it collected takes 4 years to get back. But Breakthrough Starshot is real. It's being seriously researched, funded by real money, with serious scientists doing serious work on the engineering. And it's telling us something important. The only near-term, physically plausible way to send anything to another star in a human lifetime involves sending something vanishingly small, impossibly fast, with no way to stop. And even that requires technology significantly beyond what we currently have. That's where we are. That's the state of interstellar travel as a serious engineering challenge. A chip-sized probe on a reflective sail, 20 years of travel, at 20% of the speed of light. No deceleration. A flyby. And a 4-year wait for data. That's the best plan we have for the nearest star. And it doesn't exist yet. There's one more aspect of cosmic distance that strikes differently the more you sit with it. The radio silence. We've been transmitting radio waves since the early 20th century. Radio broadcasts, television signals, military radar, communications. All of it radiating outward from Earth at the speed of light in all directions. Our radio bubble, the expanding sphere of radio signals humanity has sent into space, is now about 240 light-years in diameter. The signals closest to the edge are the first faint radio transmissions from the 1920s, traveling for 100 years. 200 light-years. In a galaxy 100,000 light-years across. If there's a civilization 300 light-years from Earth, they've received none of our signals. Nothing we've ever transmitted has reached them yet. If there's a civilization 50 light-years from Earth, they may have received early radio transmissions. But nothing from the television era. And the signals, even if they're detectable, are extremely faint. The inverse square law again. Radio signals, spreading over a sphere 200 light-years in radius, are diluted by the square of that distance. Detecting the unintentional radio leakage from Earth at a distance of 100 light-years would require an antenna many times the size of Earth. Something we haven't built. Something that, as far as we know, doesn't exist. If other civilizations are listening for leakage radiation from other worlds, the way SETI listens for signals from other civilizations, they'd have an extremely hard time detecting us. We're not broadcasting loudly. We're leaking faintly. And the galaxy is big enough that faint leakage barely reaches anywhere. The Drake equation is a famous formula that estimates the number of detectable civilizations in the Milky Way. Frank Drake formulated it in 1961. It multiplies together a series of factors. The rate of star formation, the fraction of stars with planets, the fraction of planets that could support life, the fraction where life actually develops, the fraction where life develops intelligence, the fraction of intelligent species that develop detectable technology, the average lifespan of a technological civilization. Many of these factors are unknown, but even optimistic estimates suggest that detectable civilizations might be separated by thousands of light years. Thousands of light years. A signal from one civilization to another would take thousands of years to arrive. A response would take thousands of years to return. The minimum round-trip communication time between civilizations, even if they exist, even if they're transmitting, might be measured in thousands of years. Thousands of years for a single question and answer. The Milky Way could be full of civilizations, and we might never know it. Not because they're hiding, not because they don't want to communicate, because the galaxy is so large that the signals they're sending take thousands of years to reach us. And the signals we're sending take thousands of years to reach them. The Fermi paradox, the famous question of why we haven't detected alien civilizations yet, might have the simplest answer of all. The galaxy is so big, and the distances are so vast, that even radio waves traveling at the speed of light take so long to cross between stars that the absence of detected signals doesn't tell us anything meaningful. We've been listening seriously for about 60 years. Signals from civilizations 1,000 light years away couldn't have reached us yet. We would need to listen for 1,000 years before we'd hear from anyone 1,000 light years out. The distances impose a fundamental limit on our ability to detect each other. Not just our ability to visit, our ability to know. That's the deeper implication of cosmic distance. It doesn't just prevent travel, it prevents knowledge. The universe may be full of life and intelligence and civilization, and the distances may be so large that we will never know it. Not through any failure of effort, not through any limit of technology, through the sheer scale of the cosmos itself. And yet, science has found a way around some of this. Not around the distances, around the limitation of only knowing about things whose light has reached us. When two massive objects move, they create ripples in space-time, gravitational waves. Predicted by Einstein in 1916 as a consequence of general relativity. For decades, they were purely theoretical. The waves are real, but they're extraordinarily small. Even the most violent events in the universe produce waves that, by the time they reach Earth, have stretched and compressed space-time by an amount smaller than the diameter of a proton. Smaller than a proton. Detecting something that's small seemed essentially impossible. But the LIGO Observatory achieved it. The Laser Interferometer Gravitational Wave Observatory. Two L-shaped detectors, one in Louisiana and one in Washington State. Each one has two arms, each about 2.5 miles long. A laser beam is split and sent down each arm. When a gravitational wave passes, it stretches one arm and compresses the other by an infinitesimal amount. The laser beams, returning and interfering with each other, are sensitive enough to detect that change. The system can measure a displacement smaller than 1/10,000th the diameter of a proton. On September 14, 2015, both detectors registered the same signal. Two black holes, each roughly 30 times the mass of the Sun, had orbited each other for billions of years, spiraling closer and closer as they lost energy to gravitational radiation. Finally, they merged. In the final fractions of a second of the inspiral, they were moving at a significant fraction of the speed of light. The merger released an enormous burst of gravitational waves. The event happened about 1.3 billion light-years away. The waves crossed 1.3 billion light-years of space, and they arrived at Earth as a signal lasting about 1/5 of a second. A rising chirp, detected simultaneously by both LIGO instruments. The discovery earned the Nobel Prize in Physics in 2017. Since then, dozens of gravitational wave events have been detected. Two neutron stars merging. Black holes of various masses combining. Each event a snapshot of some catastrophic cosmic collision. Each one happening millions or billions of light-years away. Each one sending ripples through space-time that cross those distances and arrive at our detectors. Gravitational waves don't interact with matter the way electromagnetic radiation does. They pass through everything, through the entire Earth, through the Sun, through galaxies. Nothing stops them. Nothing absorbs them. They carry information about the most violent events in the universe, directly, without any intervening matter blocking them. And because they travel at the speed of light, they tell us about events as they were when the waves were emitted. But they give us a new sense, a new way to observe the cosmos. Not just in light, in space-time itself. End quote. The universe is not just visible. It rings. Every black hole merger, every neutron-star collision, every violent gravitational event sends ripples through the fabric of space-time, and we're beginning to hear them. Future observatories, like the planned LISA mission, a space-based gravitational wave detector with arms about 1.5 million miles long, will be sensitive to lower-frequency gravitational waves. They'll detect the slow in-spiral of supermassive black holes as galaxies merge, and, potentially, the gravitational wave background from the Big Bang itself. The primordial gravitational waves created in the first fractions of a second of the universe, if they exist, and if we can detect them, would reveal physics from epochs we cannot observe in any other way. Because the universe was opaque to electromagnetic radiation for the first, roughly 380,000 years. Photons couldn't travel freely. The early universe is hidden from telescopes. But gravitational waves would have passed through that opaque early universe and continued to the present day. Detecting the Big Bang's gravitational wave signature would open a window into the universe's first moments that no telescope can ever see. Distance, in this sense, is time. The farther the signal originates, the older the information it carries. Gravitational waves from the Big Bang itself are 13.8 billion light-years old, crossing from the beginning of time to us. The distances in space are not just obstacles. They're also a deep archive, a record of the universe's history, and we're slowly learning to read it. One more number deserves attention before we step back and take it all in. The cosmic microwave background, the oldest light in the universe. The thermal afterglow of the Big Bang. Roughly 380,000 years after the Big Bang, the universe had cooled enough that electrons and protons could combine into neutral hydrogen atoms. Before that moment, the universe was a dense, hot plasma. Photons couldn't travel more than a short distance before being scattered by free electrons. The universe was opaque, like looking into a fog. When neutral atoms formed, the photons were suddenly free to travel. They streamed out in all directions. They've been traveling ever since. Those photons are still here. They've been traveling for about 13.8 billion years. The expansion of the universe has stretched them. When they were emitted, they were visible and infrared light. Now, they've been redshifted all the way down to microwave frequencies. The cosmic microwave background. It fills the entire sky. Every direction you look, coming from all directions equally. A perfect glow at about -454 degrees Fahrenheit, about 2.73 degrees above absolute zero. The residual warmth of the Big Bang stretched and cooled over 13.8 billion years. The COBE satellite mapped it in the 1990s. The WMAP satellite mapped it in greater detail in the 2000s. The Planck satellite mapped it in exquisite detail in the 2010s. And what those maps show is extraordinary. The cosmic microwave background is not perfectly uniform. It has tiny temperature variations, hot spots and cool spots, variations of about 1 part in 100,000, incredibly small. But those tiny variations are the seeds of everything. They are the traces of the quantum fluctuations in the density of the very early universe. The regions that were slightly overdense when the cosmic microwave background was emitted. Those regions eventually became the filaments of the cosmic web, the galaxy clusters, the galaxies, our Milky Way, our Sun, Earth, you. The pattern of hot and cold spots in the cosmic microwave background is a direct physical image of the quantum fluctuations that generated all cosmic structure. By measuring those fluctuations precisely, astronomers can determine the age of the universe, its geometry, its composition, the fraction of dark matter and dark energy, and many other fundamental properties. The cosmic microwave background is the universe's baby picture, and it comes from every direction. From a sphere roughly 46 billion light-years away, in every direction, the photons in the cosmic microwave background have been traveling since the universe was 380,000 years old, for over 13.8 billion years, through the formation of the first stars, through the assembly of the first galaxies, through billions of years of cosmic evolution, through the formation of our solar system, through the rise of life on Earth, through all of human history, still traveling, still crossing the universe, and arriving at our detectors now, today, carrying information about the state of the universe when it was 380,000 years old. The distances in space aren't just large. They're a record, a ledger, a history of the universe written in the time it takes light to travel. Every observation is a journey into the past. Every distance is a timestamp, and together they tell the story of everything that has ever been. Go outside on a clear night. Find the darkest place you have access to. A field away from the city. A hilltop. A beach at midnight. Somewhere, the sky opens up. Look up. Every point of light you see is a sun. Some are dim red dwarfs. Some are brilliant blue giants burning through their fuel in just a few million years. Some are older than our sun. Some are younger. Almost all of them almost certainly have planets. Every point of light is a star and probably has worlds orbiting it. And every single one of those stars is separated from you by at minimum a few light years, meaning the light entering your eye right now left those stars years or decades or centuries ago. Some of what you're seeing doesn't exist anymore. The star burned out. The light is still traveling, still arriving, still entering your eye. You are receiving messages from objects that have changed or ended, and you'll never know about the changes until the new light arrives. If you can find the Andromeda galaxy, the faint, elongated glow in the northern sky on autumn evenings, look at it. Hold your gaze there for a moment. The photons hitting your retina have been traveling for 2.5 million years. They left a galaxy of 1 trillion stars before our species walked the Earth. They crossed 2.5 million light-years of expanding universe, passing through the nearly perfect vacuum of intergalactic space, dodging dust grains and gas clouds and the faint photon backgrounds of other galaxies, traveling for 2.5 million years at the fastest speed the universe permits. And they just arrived. At you. At this moment, that smudge of light is the most distant thing the unaided human eye can see. It's the nearest large galaxy to us, and it will never be visited. Not in any time scale our civilization can meaningfully contemplate. That is where we are. One planet, one star, 25 trillion miles from our nearest stellar neighbor, 2.5 million light-years from our nearest galactic neighbor. Surrounded by a cosmos of 2 trillion galaxies we cannot reach. Inside an observable universe, 93 billion light-years across. Inside an actual universe that is almost certainly vastly larger. The distances in space are worse than you think. They are, genuinely, worse than you can think. And that's what makes looking up at them every night something close to sacred. If tonight changed something in how you see that sky, even slightly, that's what this was for. Hit the like button or subscribe if you want to keep making journeys like this one. It keeps this channel going. And the next time you step outside on a clear night and look up at those points of light across the dark, remember that you are not looking at a ceiling. You are looking out through a window into an ocean so deep, so old, so incomprehensibly wide that no language has the words for it. We just do our best. And we keep looking up. Good night.